Right, in this tutorial we're going to have a little look at how you might set up a motion simulation inside SolidWorks. So you would normally do this with an assembly because it's the relative motion between various parts. So you can't really do a motion study inside an individual part. You have to have an assembly of parts so that you can move them relative to each other. So what we're going to use as an example here is the bottom end assembly of an internal combustion engine. So you can see that on the screen. We're just going to spin this crankshaft at a certain number of RPM, and obviously that will cause relative motion of all the other parts. The reason that that will occur is that mates have been inserted into this assembly to hold these parts relative to each other in a realistic manner. So if we just have a quick look at some of the mates, the main one here is the crankshaft, how that's been mated in place, and there's been an axis inserted into this assembly. That was kind of the starting point. That axis has been placed relative to the primary planes within the assembly, so the front plane, top plane and right plane have been used to place that axis. You can see that axis kind of highlighted here, and then the crankshaft has been brought into the assembly, and the crankshaft has been placed relative to that axis, amongst other things. But the fact that we've used an axis allows us to rotate the crankshaft around that axis. One other thing to note is there is an angle mate that's also been placed on the crankshaft, and that's just for convenience really. It's just to stop me from accidentally dragging that crankshaft out of position as I'm working on things. And you can see that angle mate there. If I wanted to be able to drag the crankshaft in a realistic manner, I could just suppress that mate, and then I can drag the crankshaft to wherever I need it to be. But it's more convenient as I'm working on things just to have that mate active. And the fact that it is an angle mate means that I can place the crankshaft very accurately at any rotational point. So let's say I wanted it 2 degrees out of alignment. I could change that value to 2 degrees and then do a rebuild on the assembly, and you can see the assembly kind of moved slightly into that new position. So that's quite useful. I'll actually undo that 2 degrees because I want it to sit at top dead center, and then just do a rebuild again. So that's our starting point. And obviously all these other ancillary parts, all the conrods and the conrod caps and the pistons also have corresponding mates that have been put on those. And the way that this assembly is being set up is all those other parts that I just talked about that aren't the crankshaft have actually been defined within their own small subassembly. So you can see I've selected one of those subassemblies here, and if I open that up, we can see what parts are included within that subassembly. I've actually left it in an exploded state here, so I'm going to just reverse that. There we go. So these parts have been held as a subassembly, so they've had mates placed between them, again in a realistic manner to kind of hold them relative to each other. So I'm browsing through some of the mates that are within the piston. There's some concentric mates between various geometry on the piston and the piston pins, and various oil rings and compression rings. So yeah, that's how this assembly's been set up. So I don't need this subassembly open. I'm going to close that down. What I want to do now is I want to begin the process of creating a motion simulation of this assembly. So before I begin that process, I just need to check in SolidWorks add-ins, is the motion simulation add-in switched on? Yes, it is. And then because I've created motion studies within this assembly previously, they're already listed down at the bottom of the screen here. I have two of them that I've been working on previously. I have one just with the default name of Motion Study 1, and then I have a second one that I've named 60 RPM. So I'm going to create a new one here, but you probably won't have to do this. You can just go into Motion Study 1 and just do the steps that I'm about to show you. But what I'm going to do is I'm going to right click on Motion Study 1, I'm going to say create a new motion study. I'm now in a blank new motion study. As I say, you'll be able to do this with Motion Study 1 because you won't have previously created any motion studies, so that's fine. And then because I'm doing a full simulation and study here, I'm going to change this option here from animation to motion analysis. And generally speaking, animation is the most simplistic motion that you can create, and full motion analysis, or just motion analysis, is the most realistic or the most detailed. And then we have basic motion, which is kind of somewhere in the middle. So we want full motion analysis. And then the first thing I'm going to do is I'm going to find that angle mate that's restraining the crankshaft and not allowing it to spin, and I'm going to suppress that. So I'm going to have a look inside the crankshaft here. I'm going to have a look inside it, the mates folder within there, and I'm going to right click and say suppress that mate. So that will allow the crankshaft to rotate now. And in order to make it rotate at a speed that I require, I'm going to place a motor on the crankshaft to spin it at whatever speed I need. So the way that we do that in motion analysis is we click on this icon here, motor icon. There's two types of motor. There's a linear motor that can move in a straight line, or there's a rotational motor. So make sure you have the correct one selected here. And then the easiest way to apply this is just to pick a circular edge around which you want that rotation to occur. So I've just picked this circular edge on the end of the conrod here. And then you've got the option of changing the direction by clicking on this reverse direction icon here. I was happy with the direction. It doesn't really matter too much in this example. And then you can set a speed that you want it to rotate at. So this value doesn't really matter too much at this point. We can always come back in and edit these values later on. So I'm just going to pick an arbitrary value, let's say 1000 RPM, and then click on OK. And then in order to see the effect that that motor is going to have within our motion simulation, we have to calculate the motion analysis. So there's the calculate button right there. And then the motion will appear kind of fairly choppy or fairly low frame rate as it's calculating. But once it's calculated the motion analysis, you can play it back and the frame rate will be much higher. So this is just a kind of rough preview of what that motion will create in terms of the motion of the other components within the assembly. So this can take a little while. I may pause the video here and just kind of unpause it when we have finished this. So here we go, the motion analysis is now completed, or it's calculated, and in order to run what we've just calculated, I'm going to press this icon here. So that will run through what has just been calculated there. And it will continually run through it because I have this loop option selected here. If yours isn't continuously running through, you can set that option here, and then I can stop the animation and I can kind of search for any point within that animation by dragging this bar along here. Now my time period by default in these motion analysis setups is set to 5 seconds. I don't have to accept that. In this case nothing much is changing over the 5 seconds, so it's a little bit pointless to spend all that calculation time that we had to spend in order to calculate the full 5 seconds. So I'm going to click and drag the length of this animation by holding down on this black diamond, and let's drag it all the way back to 1 second. And then, because I'd like to see in a bit more detail or finer graduations of time within my 1 second, I'm going to go down to the bottom right here and say zoom to fit. And that kind of blows that 1 second up to almost fill the entire screen there at the bottom of the screen. So that just allows me to search that 1 second a little bit in finer detail. So the graduations are a little bit smaller now. So we've got our assembly running at that speed. That's all fine. But we very often need some quantifiable data out of these motion analyses. So the data that I'm going to gather from this motion analysis is for a given point on one of these conrods, what is the acceleration that the conrod is experiencing in vertical direction and in the horizontal direction. So in terms of the coordinate system of the assembly, that would be y and x. So what acceleration figures is that conrod experiencing, or more specifically, is a specific point on the conrod experiencing? So it will obviously be a combination of the two, because obviously up at this end of the conrod, its primary movement is going to be in the y direction, because it's restrained, because it's attached to the piston here, which can only move up and down. But down at this end of the conrod, it's experiencing a combination of acceleration in x, so that would be horizontal as we're looking at it, and accelerations in y. And when I say accelerations, I mean acceleration and deceleration. So obviously it has a furthest extent that it moves down in y, and then it has a furthest extent that it moves up to the top of its limit in y. And in order to get from one to the other, if we observe it starting from rest, it has to accelerate up to a maximum value, and then it has to start decelerating as it gets towards the bottom of the stroke there. And likewise for the horizontal accelerations as well. So we're going to plot those accelerations on a specific point on these conrods. So let's do that now. If we want to plot any sort of value as a graph, then this is the icon that we initially click on to set these plots up. And then there's various categories or broad categories here that we can choose from. I've already said that we're going to plot an acceleration figure. So that would be a subsection within this displacement, velocity and acceleration option. What I would encourage you to do is, after we've set this up, come back in here and see what other values you can plot, because there's multiple values that this system will allow you to plot, and depending on what data is most useful to you, this can be a very useful way of obtaining that data. But as I've already said, we're looking for an acceleration. So what sort of subcategory? It's going to be a linear acceleration, because we're kind of resolving this motion into just its linear y component or its linear x component. So it's a linear acceleration. What is this next box asking for? Well, if you hover over the box, you'll get a tool tip that will pop up telling you, or giving you a bit of a clue as to what it's asking for. Select one face, one vertex on a part, or one mate or simulation element to plot a result. So this is what I was talking about earlier. This is the point on the conrod that we're going to get our acceleration figures for. So I'm going to pick a point down near this end of the conrod, because as I said previously, this end of the conrod is kind of the most interesting to us, because it has movement in X, but it also has movement in Y, whereas the other end of the conrod is limited to just movements in Y. And then obviously the nearer you are to this end of the conrod, the more limiting the X movement is going to be, and then the more near to this end of the conrod, the more X movement you're going to experience, and it kind of fades from one to the other throughout the body of the conrod. So I'm going to pick a point at the kind of limit over here, so maybe one of these vertex points here would be quite useful. So that's the point that I'm interested in. How is that accelerating that point in X and in Y? And then by default, this system will use the assembly X and Y coordinate system. And if that figure is going to be useful to you, then by all means, you don't need to enter anything into this last box. But because of what I intend to do with my plot figures, that is, I intend to use them in a static part analysis of just the conrod part, then it will be more useful for me to not use the assembly coordinate system, but to use the internal coordinate system of the conrod itself. Because if I'm going to be doing a static simulation where only the conrod part is being considered, then I won't have access to the assembly coordinate system. And more than that, the conrod is kind of rocking around relative to the assembly coordinate system. So the assembly coordinate system and conrod have got relative kind of rotational movement between them. So it's, I could envisage a situation where using the assembly coordinates would be useful, but I suspect most of the time using the internal coordinate system of the conrod itself would be more useful. So I'm going to select this last box, and then again, if you hover over it, it kind of tells you what it's looking for. Component to define X, Y and Z directions, and I'm just going to pick the conrod itself. And then I get a preview of what X and Y and Z, or what direction they are pointing relative to the conrod itself. So the last thing that I need to choose here is I'm going to do this process twice. I'm going to do it once for the X component, and then I'm going to do it again for the Y component. So what I'll end up with is two graphs that run over my 1 second motion analysis, and they will show how the X and Y acceleration figures rise and fall throughout that time period. So this one's going to be the X component, so I just need to click in this box here and say X component. So this is the side to side one, and then click on OK. Those figures will be plotted, and then you can kind of drag this plot so that it's a little bit more legible, and you can see the maximal and minimal extents that those acceleration figures reach. So that's relatively useful in terms of using those acceleration figures within a static part simulation. So let's run through that again, except this time let's plot the Y component of those accelerations. So same process, just as we did before. I'm going to select the same point. I'm going to use the coordinate system that's internal to the part itself, and then I'm going to say I want to plot the Y component this time, and then click on OK, and I get a kind of similar looking graph, but this time for the Y components. And if you're wondering how to get the X component graph back on the screen, because I closed that graph down just to tidy the screen up a little bit, if you scroll down to the bottom of the motion analysis manager here, there's a folder called results, and the two graphs are listed there, and if they're grayed out as mine are now, then they're hidden. and if you want to show them, you can just right click on either one of them and just click show plot like that, and then you can compare them to one another as well. So one last thing that I'm going to do, I'm just going to, so I don't lose track of what these values relate to, I'm going to name this acceleration X, or ACC-X, and I'm going to name this ACC-Y. So that's the broad outline of how you set up these plotted results. And as we saw in those menus, there are a multitude of values that you have access to be able to plot. And I would encourage you to kind of play around with this tool and see what sorts of other things that you can plot. You can plot things like contact forces, momentum values, velocities, angular velocities, position of center of mass of the part. There's lots of values in there that can be useful, and the only real way to get an appreciation of that is to experiment a little bit with them. But one last thing, or a few kind of final thoughts on this process. So if I just show one of these graphs, let's show the X. Having used this tool reasonably extensively in the past, it occurs to me on this graph that there's not a great deal of detail. And what I mean by that is it seems to be jumping in a very linear fashion from its minimal value on this graph to its maximal value. So what I mean by that even more specifically is that is a straight line between those two values. And I would expect this to look a little bit more like a sine wave. So that leads me to believe that the number of frames per second that the system is calculating at is too coarse. There's not enough frames or not enough calculations per second of time to fully reflect the situation that would occur if the real assembly was spinning at 1000 RPM. So I'm going to play around with that setting a little bit and see if my suspicion is correct. So the way that we do that is this little icon here. This allows us to set up some certain settings for the overall motion analysis, and all I'm going to do is I'm going to put that frames per second up to shall we go up to 500 to begin with and see what difference that actually makes. And then because we've changed something, we have to recalculate, so I'm going to click on the calculate button again, and it will run through its calculations. So that did take quite a while to calculate, but it does seem to have had the effect that I was looking for, in that this graph now more closely resembles a sine wave, more so than the last one did. What I would be tempted to do at this point is, given that nothing much is changing throughout the whole time period, I could relatively safely reduce the time period right down to a much shorter time period, say 0.2 of a second, and that will speed up the calculation time. So if I just do a little experiment now, yeah, that's calculating, or it's going to calculate a lot quicker, because it's only required to get to 0.2 of a second now. Yeah, and that's more like the graphed shape that I would be expecting. There's multiple points there, and if you click on the graph itself, you click on the actual plot, the line itself, you can see the time calculation points. And I suspect before we only had a calculation point at every peak and every trough, whereas now we have all these other points that have been calculated and graphed, giving us a much finer picture of what is actually going on during this time period. And we can be kind of more, or the figures that we are getting here can be relied upon a little bit more. We were getting some odd spiking down here on the original graph, which we don't seem to be getting now, because what I'd expect, because this end of the conrod is largely tracing a circular path, or almost entirely tracing a circular path, I would expect its acceleration in positive x direction to be equal and opposite to its acceleration in negative x direction, and that is almost exactly what we're seeing here. There's a slight discrepancy, but yeah, it's within acceptable limits, which is what I'd expect to see. So at that point, you could now use these acceleration values in a static study on the conrod, because obviously as the conrod's moving around at this high rate of velocity, and the velocity is increasing and decreasing, therefore it's experiencing the effects of that acceleration and those inertial effects. You could feed those into a static analysis, the acceleration figures, these acceleration figures specifically, and the ones in the y direction, and you could see what effect the mass of the part itself will have under that acceleration, because obviously the internal forces that part experiences will be contributed to because the part itself has mass, and because it's experiencing various accelerations. So force equals mass times acceleration. So the mass of the part won't change. The system knows the mass of the part if you've set the material correctly. And now you can supply an acceleration figure as well. So yeah, motion analysis, motion studies, quite a useful tool within SolidWorks to gain information such as the accelerations that we've just plotted.